kind of go backwards from what we did on Friday. If you remember, on Friday, what we did is we graphed the exponential function, then we graphed its inverse, and then we gave it a name, and depending which kind of function we were working with a logarithm, spelled log, or we also looked at a natural logarithm, which was abbreviated with the ln. And what we learned about exponential functions and logarithmic functions is that they were inverses. And if you remember, when you're dealing with inverses, the x values and the y values change. And the x values and the y values correspond to domain and range of functions. So once you have the domain of a function, its inverse will become the range of the inverse. I think I said that right. So the domain of the regular function will become the range of the inverse, and the range of the original function will become the domain of the original function, of the inverse function. But what I want to look at specifically here today is that the domain of a parent logarithmic function is 0 to infinity, and the range of the parent logarithmic function is all real numbers, negative infinity to infinity, because we're going to be graphing logarithms here in a couple of minutes. But before we get to that, let's learn, or try to learn here, there we go. Let's learn how to find the domain of the function algebraically. And what we need to notice in A, B, and C here is that they have log in there. And what's going to happen is that on these functions, this part of the logarithm, sometimes referred to as the argument of a logarithm, has to be positive. And that goes back here to this. The domain of the parent logarithmic function is 0 to infinity. And 0 is not included because it has a parentheses in it. So what that means is it's anything greater than 0 onto infinity, which is where I get the must be positive. So when we set this up to come up with the domain, what we do is we take the x plus 3, and we set it greater than 0. We didn't say greater than or equal to, we just said greater than 0. We can subtract 3 from both sides. And our domain of log base 2 of x plus 3 is x is greater than negative 3, also known as, in interval notation, negative 3 to infinity. When we come over here, I'm going to skip B for a moment and jump over here to C. On C, this value still must be positive. 0 to infinity is the domain of our logarithmic function. It doesn't matter the base. Over here we have log base 2. Here we have log base 5. Here we have log base 1/2. Doesn't matter what the base of the logarithm is. It's the argument part of the function, the 2x minus 5, has to be greater than 0. And we can solve that by adding 5 to both sides. So we get 2x is greater than 5. Divide both sides by 2, and we get x is greater than 5/2. If we want to write that in interval notation, it would be 5/2 to infinity, parentheses. Infinity always has a parentheses in interval notation. The 5/2, it's greater than. There's no equals to, so we have parentheses there. But the reason that I skipped B here for a minute is yes, this value still must be positive. But what happens when we square a number? And if we get more specific, if we square a positive number, what kind of answer do we get? Like if you square 4, you get 16. If you square 5, you get 25. If you square 10, you get 100. What happens if you square negative 4? What kind of answer do you get? Positive 16. Or if you square negative 5, you get positive 25. Or you square negative 10, you still get positive 100. Because this function is squared right here, not only is it x is greater than 0, but if we happen to have a negative value that we put in there, when we square it, it still became positive. So in terms of our domain on this function, it would be negative infinity to 0 joined with 0 to infinity. So now that we've looked at how to deal with the domain, let's look at another problem here with the domain, but let's add some more work to it, but not for the domain here. First of all, it's f of x equals 3 times log of x minus 1. Our first step here is that we want to figure out what is the domain of this function. So what we're going to do is we're going to take this value here of x minus 1, and we're going to set it greater than 0. We can add 1 to both sides. And when we do, we're going to get x is greater than 1, which is our domain. And if we write this in interval notation, that's the same thing as 1 to infinity. One more time. So part B. What does the 3 in front of the function do to the function when we graph it? What's the transformation there? It's going to be a stretch. What kind of stretch? Yep. It's going to be a vertical stretch. We also have minus 1 inside the function. What does that do to our function? How do we transform it? We're going to go right. So when we come down here to part C, let's type that in our calculator. And I'm going to go back and take something out of mine, but 3 log of x minus 1. If you have an Inspire, you need to type a 10 in for the base. But when we look at the picture here, first of all, when we turn on the function and look at the picture, there's our picture. So we kind of know what it's going to look like. It doesn't just stop there where our blue part of our graph stops. But when we go over here to the picture, and I scroll through to get a couple of values, we see the 2, 0, which is a nice function, a nice value for us to use. But as we scroll a little bit more on our table, it doesn't quite fit on the graph, but we can make it work for us. We see another point, 11, 3.
Which one do you use the... Oh, wait.
I just went to this, the log to the left there. Just the actual log button. We went to the table. So our function looks something like that. And if you think back to the key points that we learned on our parent functions, it makes sense because one of our points on the logarithmic function was 10, 1. We moved it to the right 1, and then we stretched that vertical distance of 1 up to 3. There's our function. But the question is, what's the range of this function? And maybe you need to look above on your paper again. Well, the domain of the parent logarithmic function is 0 to infinity, and the range is all real numbers. Is anything going to change for us? Nope. We're going to have the range. Let's deal with the intercept here. Do we have any intercepts in our graph? And it looks like we have a value of 2, 0. Do we have an asymptote in here? And we actually do. It's a vertical asymptote at x equals 1. Makes sense because here's our domain. X is greater than 1, so it can't equal 1. So this is, the red line is the place where our graph is getting closer and closer and closer to, but never quite touching. What we want to graph now is we want to graph the inverse function, and we need to find the inverse function to be able to graph it. The function that we're working with is going to be y equals 3 times the log of x minus 1. Same problem that we started with back there in A. Remember, when we're dealing with the inverse, that we're going to switch the domain and the range. So x is going to go where y went, and y is going to go where x went. So it's going to be x equals 3 times log of y minus 1. Once we switch our x and y, what we want to do is we want to solve for y. So we need to isolate our value that we're solving for as much as possible. So this is 3 times the logarithm. So we're going to have to use the inverse operation to divide by 3. So now we're left with x divided by 3 equals the log of y minus 1. Well, we need 2 more pieces of information to be able to solve this, or solve this equation for y. And the first one is the base of log, when it's not written, is a 10. This is a common logarithm. So when the base is not written, it's a 10. And secondly, what we need to do is, in order to isolate our variable, we need to convert this logarithm into exponential form. So if you recall, what's going to happen is we're going to take this value of 10, and we're going to go around here. So it's going to be 10 to the x over 3. The logarithm is another way of writing an exponent. So what this function equals is an exponent. And that equals y minus 1. 10, here's our exponent, the x over 3, equals our argument over here of the y minus 1. And what we're trying to do is we're trying to solve for y. So we can finish by adding 1 to both sides. And we end up with 10 to the x over 3 plus 1 equals y. And that's our inverse. And now we want to graph that. So we'll go back into our calculator. In our second graph here, and actually I'm going to put it down here in the fifth. That way it'll match the colors. We have 10 to the x over 3 arrow, because get out that exponent, plus the 1, and we can graph. So there's our picture. A nice little feature of the calculator is that we can leave that blue graph in there without actually looking at it. We can leave the equation in there. We can go over to the equal sign and we can highlight it, hit enter, and now when we graph, we're only going to see the green graph. And the only reason that I want to do that is so that I can look at the table with it being just the table for the green functions, to get some values there. And remember what we just did. We just found the inverse. So on our blue graph, we have the point 2, 0. So even though I can't see it on my table right now, I'll pull it up here in a minute, we can have 0, 2. Because we switched the x and the y. One of the values that I can see right now here is this 3. So there's the 0, 2. But we also have 3, 11, which we had 11, 3 in our blue function. So 3, 11. And then I may just want to get one more point here, maybe negative 1. Negative 1 is roughly 1.5. And there is our picture of our inverse function, the inverse of our logarithmic, which is an exponential. And let's identify some features here of this. First and foremost, are these graphs a reflection over the line y equals x? Let's look at y equals x. It goes from the bottom corner, bottom left-hand corner, to the upper right-hand corner. If we fold our graph along that line, will that blue graph land on the green graph? Yes. So they do reflect over the line y equals x. That's a good sign. Remember, we found the domain back here in A. It was 1 to infinity, which means down here that our range is going to be 1 to infinity, because we switched. Our range of our logarithmic function in part D was negative infinity to infinity. It's going to become the domain of our inverse here, which is negative infinity to infinity. Now our blue graph had an asymptote. It had a vertical asymptote at x equals 1. Do you think we have a asymptote in our green graph? What do you think it is? Y equals 1. Right along here. Horizontal. Now, let's look at a natural log function. It's k of x equals negative the natural log of x minus 2. And what we want to do is we want to write this, we want to find the domain, first of all. So when we start with this, again, it's going to be x minus 2 is greater than 0. When we add 2 to both sides, we get x is greater than 2. And in interval notation, then that means 2. to infinity. Well, we have two transformations occurring on this function. The first one, there's a negative in front of the function. And what happens when there's a negative in front of the function? How do we reflect? Over which one? Next. We also have minus 2 inside the function. How do we transform that? Or what does that do? Move our function right. 2. So now we're going to go ahead and graph this function. So if we go back in here and we clear out the first function, and I need to clear out this function. And we can type in our function here. The natural log button is the third, it's to the far left, it's the third button up. So it's going to be negative natural log of x minus 2. And then we can look at the table. And in fact, we can even look at the graph. I'm going to go for table. Oh, it's graphed after all. So there's a picture. And again, just like that last one, remember that it doesn't just stop there. It's just that the calculator can't make the line thin enough to keep going. But we can look at some values here since we're going to graph this. And 3, 0 is going to be a point for us to graph. So we've got 3, 0. And if we look here at a couple more, maybe, nothing's going to be super good, but how about 5 is negative 1.1, 4, 5, negative 1.1. Did I get that right? I didn't get that right, did I? Oh, I did. That's good. So there's our picture of our function. Again, we're dealing with a logarithmic function, so what's the range of this? And it's still going to be negative infinity to infinity. Do we have any intercepts here? We've got 1, 2, 3, 0. We've got an x-intercept. Do we have an asymptote? And we do. And I think it's actually here at x equals 2. When we take a look now at our function, which is y equals negative the natural log of x minus 2, what we need to know about a natural logarithm is that the base of it is e. If nothing's written and it's understood, if you look at your calculator button, it coincides. If you push second, it gives you an e to the x on there. And what we're going to do is we're going to find the inverse of the function. And the way that we find the inverse of the function is we switch the x and the y. So it's going to be x equals negative the natural log of y minus 2. We'll get that e back in to the problem. We need to isolate the variable that we're going to be solving for, which is y. We need to solve for y. And it's negative times that natural log. So we're going to divide both sides by negative 1. When we divide by negative 1, we're left with negative x equals the natural log of y minus 2. And again, the base of the natural logarithm is e. And now what we need to do is we need to rewrite this function instead of in logarithmic form, in exponential form. So when we do, a logarithm is another way of writing an exponent. This becomes e to the negative x, whatever the logarithm equals is the exponent, equals y minus 2. And if we can get it in that format, then we can finish the problem. Because remember, what we're trying to do for our inverse is we want to solve for y. So we're going to add 2 to both sides. And we get e to the negative x plus 2 equals y, which is our inverse. And I think, didn't I do a different letter here? K. K to the negative 1. There's our inverse. So now that we found the inverse, we're going to type this equation into our calculator and graph it. Second ln to the negative x arrow plus 2. And we can look at our table, come up with some points there, and actually I'm going to go back to my y equals and go over to the equals and press enter so my first function doesn't graph. And what we can see is we've got 0, 3 over 0 up 3, and we can graph a couple other points. Remember, this one was 5, negative 1.1, so negative 1.1, 5. And let's see if we see any other points that we can use. And negative 1.15 we're not going to be able to see on here, but negative 1 and 4.7 seems to be reasonable. Negative 1 and 4.7. Let's see what positive 1 is. Positive 1 is 2.4. Here's a picture. The question is, does this function reflect over the line y equals x? Remember, goes from the bottom left to the upper right hand corner through the origin. I'm off just a little bit, but the answer is yes, they do reflect over the line y equals x. We have an intercept of the inverse at 0, 3. It's a y-intercept. Our domain of our function, remember, is going to be coming from our range, which is going to be negative infinity to infinity. And our range of the functions coming from our domain, which the domain of the original function was 2 to infinity, so our range is going to be 2 to infinity because the x values and the y values switch. And lastly, do we have an asymptote? Well, we had x equals 2 originally, so we're going to have y equals 2 for our asymptote.